Optimization problem.
Do we need an optimization problem? Okay. We want to look at the volume. We want to look at area.
So there's one on in the packet that had
Yes?
find the minimum area of the poster. I think. There is,
I have no idea which one.
number 34
34?
on 333.
Yeah, we did 33, which is similar to the poster problem. Yeah, we did 33 in class.
So when it's, because 33 was
Okay, let's take a look.
to find the min.
That's fine. So, okay. So a poster is to have an area of 180 squared centimeters with 1 inch margins at the bottom and sides. 1, 1, 1, and 2 at the top. What dimensions will give the largest printed area? So this time this is x and this is y. And we have x times y equals 180. That's one option. Or the other option is to, so that's option number 1. And option number 2 is to consider this x and y. And then this is x plus 2. And this is y plus 3. And then x plus 2 times y plus 3 equals 180. One or the other. Both should give us the same answer. So now if you want to minimize this area, that's what we're asked, is it what dimensions? Oh, the largest printed area. So we want to maximize the area, max this area. So if we stick with that, then we have the area, which is x minus 2 times y minus 3. So this piece is x minus 2, and this piece is y minus 3. Is that okay? Yes? 1 and 1, 1 and 2. From y, I subtract 3 to get this. From x, I subtract 2 to get this, because this is 1 and 1.
I thought the margins are 1, right?
From x, I subtract 2 to get this piece. From y, I subtract 3 to get this piece. 2 plus 1 is 3. Subtracted from y. Oh, okay. You didn't know that that is the top is 2.
I thought the 2 was horizontal. I missed the third maybe.
1 inch margins at the bottom and sides at the, and a 2 inch margin at the top.
Oh, okay, that's where I missed it.
So I have to distribute xy minus 3x minus 2y and plus 6. I am given that xy is 180, and I will have to replace y by 180 over x. And I put it in here. So now the area is indeed only a function of x. So 180 minus 3x minus 360 over x and plus 6. From here, all you have to do is differentiate, set it equal to 0, and solve the equation and study the sign. Is that good enough?
Yeah, I think I just mixed up some of the signs.
Okay. So I'm adding, so this is going to be 186 minus 3x. Don't find the least common denominator because it's easier to differentiate this way. And then you set it equal to 0 to find the critical number. Is that good enough? Okay. Anything else? Anything else? Anyone? Nick? Jace? James? Okay. On Tuesday, I will be here early, so if you want to come in early, if you can, and ask more questions, that would be great. So our test is next Tuesday, okay? Okay, I will not continue with 4.9 because 4.9 may confuse you on Tuesday. So I will talk about 4.9 after the test. Okay, so let's start chapter 5. Chapter 5 deals with integrals. We're not going to define them today. So we are looking at preliminaries. Okay, so if I want to add, for example, 1 plus 2 plus 3 plus ... plus n, we have a mathematical way of writing the sum. It's a sum of the first n terms. And here's how we do that. This is what it's called the sigma notation or the summation notation. Sigma or summation notation. It's S, but it's a Greek S. It's the Greek letter S, not the regular S, the Latin S. Okay, so what does this mean? First of all, it's not complete. This is just the symbol. I have to explain or show how this turns out to be all this sum. It has to have a lower limit. The lower limit normally we use I, j, k. So from I equals 1, from the very first term till the last term, which is n. So this is the lower limit, I equals 1, or 1 is the lower limit. And what do you think n is? Very good. And then I have to write I. Let's see how this works. When I is 1, I have 1. The sum says plus. When I is 2, I have 2, and then plus. When I is 3, plus. ... Exactly 3 dots. Not 4, not 2, not 1. Exactly 3. Plus, when I is n, I have n. This happens to, and we can prove this using mathematical induction. This happens to be n times n plus 1 divided by 2. Now you can say, is there an application, an immediate application of this? A lot, many. For example, let's suppose for whatever reason you want to add numbers from 1 to 4,000. Now you can. It's 4,000 times 4,001 divided by 2. So you have 8002, 3 zeros. Just like that. You can anything you want. Okay, what about about this? If I want to add I squared from I equals 1 through n, can anyone tell us, give us a few terms? The first few, 3 terms, let's say, and the last one?
One, 2 squared, 3 squared, n squared.
Let's say if you want to add from I equals 1 through 400 of I squared, you will be able to. There is a formula for this, which is n plus 1, 2n plus 1 divided by 6. So if you want to add from I equals 1 through which number you want?
15 or 20.
Okay, 20 of I squared. All you have to do is to say 20 times 21 times 41 divided by 6. If they are squared, if you want to add the squared ones. So I'll simplify. And by 2 and I get 10, and by 3 and I get 7. So it's 70 times 41, which is 2870. All I had to do is just replace n by 20. Okay, 2 more. Let's say I want to add from I equals 1 to n 1, just 1. Can anyone give us the first 3 terms and the last one?
1, 1.
Not 1, but 1 plus, right? So this indicates, because there is another symbol, which is this. Multiplication. This is the product.
So what is it called?
Pi,
Big pi.
big pi. What does this equal to?
N times 1.
Exactly. N. Perfect. Okay, last one. Promise. I equals 1 to n from I cubed. Can anyone give us the first 3 terms?
1 cubed, 2 cubed,
Plus.
that's 3.
Awesome. Very good. There is a formula for this. Not difficult to remember. It's the same one with this for I, but everything squared. I don't like saying that to you, but we have to memorize these 4.
Something a little bit, but
The Ricola. Yeah, I don't have anything else. Sorry,
all right.
sorry. I'll be better equipped next time. Okay, so one more time, let's write them one more time. The sum of 1 from I equals 1 through n is n. In summary, the sum from I equals 1 through n from I is n plus 1 divided by 2. The sum of I squared from I equals 1 through n equals n plus 1. This is the most difficult one to remember, but once you write it 3 times, you will. And the last one is same thing, but squared. I equals 1 n plus 1 over 2, everything squared. Okay, now there are 2 properties of this summation notation. So obviously this is called a general term. So here are the 2 properties. The sum of ai plus bi from I equals 1 through n. What does this mean? When I is 1, I have a1 plus. When I is 2, I have a2 plus, and so on and so forth. When I is 1, I have b1. When I is 2, I have b2. What do you think this will equal to, either if it's a sum or a difference in the middle? Wild guess. Same with limits. Same property that we found at limits, for limits. The limit of a function plus another function is the limit of, that's it, the same thing. It's like with the limit of a function plus f plus g is the limit of f. This is not a limit. I'm just going back to the concept, the similar concept we used for limits. And there is one more, which is very familiar concept from limits as well. So the sum of a constant times ai. What do you think? Wild guess, which I know is not that wild anymore.
Constant times the sum.
Yes. Because the constant does not depend on I, on the index of the summation notation. It does not. Therefore, it can go outside. And now, let me know if you need to prove any of these using mathematical induction. If not, I'm sure you are wondering, what is this? What do we need it for? And you will see in a minute what we need it for, what is it used for. Would you like to prove any of these? I'm not going to ask you to. They, all three can be proven using mathematical induction. If you say no, then we'll continue. You trust me? Thank you. Okay. Now let's say we want to find the area under the graph of f of x equals, you want negative x squared? It will be a negative area. Let's start with a positive area. It's possible. We can have a positive, we can have a negative area, but let's start with a positive one and then we'll look at anything else. So for the sake of the argument, I'm going to choose a quadratic function because it's easy to understand. Let's say x squared plus 2. We know this graph quite well. Now let's choose an interval. For now, let's choose an interval that starts at 0 for simplicity. Is 0 to 2 okay? Okay. So when x is 0, y is 2. When x is 2, 6. Agreed? And the function opens upward. And we want to find the area under this graph between the graph and the x-axis, of course, because otherwise we have no idea. Okay. Let's suppose that our first step is to use two subintervals. So I divided the interval between 0 and 2 into two subintervals. The width of the interval will be denoted by delta x. Length, I'm sorry, I meant to write width. Width of the interval is delta x. How do I determine the length of the width of the interval if I know that I have two subintervals and the width of the interval or the length of the interval is 0 to 2? So the interval normally will be denoted by a comma b. So the delta x will be b minus a divided by the number of subintervals. So in our case, you're right. It's 2 minus 0 divided by 2 subintervals. So this is 1. So that's why we had the interval, the length, the width of the interval 1. In order to approximate the area, the question is asking us to find the exact area. We're not there yet. So I'm going to approximate the area using 2 subintervals and the rightmost point of the interval. The leftmost point and the midpoint. Okay. What does that mean? The rightmost point of the interval. So we will create rectangles. How many rectangles? 2, because we only have 2 subintervals. So here's the area of the first rectangle. Base times height. I'm using the rightmost point. Here is the right triangle, the rectangle. First rectangle on top of the first width. Here is the next one. Base times height. Please ignore the fact that my unit is not perfect. Sorry about that. I'll be more careful next time. So these two should be equal. They're not in my graph. So the area of the first rectangle, base times height, being using the rightmost point for the height. Base times height, using the rightmost point for the height. Obviously, this will be an approximation of the area, and it will be an overestimation. Why? Because I have this piece that is not under the graph, and I have this huge piece in this case that is not under the graph. So here's how we write it. The area with the rightmost point 2 subintervals is approximately, it's not exact, base times height, 1 multiplied by f of 1, plus base, which is 1, multiplied by f of 2. One more time, base times f of 1 plus base times f of 2. So let's see what we get. Now this expression equals 1 times f of 1. F of 1 is how much?
3.
Very good. So 1 times 3 plus 1 times, and f of 2 is 6. So the area is 3 plus 6, which is 9. Obviously, it's a estimation of the area. Good. Now we are going to look at the same graph. 1, 2, 1, 2, 3, 4, 5, 6. Here's the graph. But this time, the leftmost point, here it is, base times height. The next one is base times height. Is this an overestimation of the area? So this will be a left 2 approximately. Is it an overestimation or underestimation?
Underestimation.
Perfect. So now this time I have 1 base times height, which is f of 0, plus 1 times the height, which is f of 1. How much is f of 0? 2. So it's going to be 1 times 2 plus 1 times f of 1. We have f of 1, which is 3. So 2 plus 3, which is 6. I'm sorry, I meant to write 5, of course, in case you are doubting. No, I cannot make a new rule. This 2 plus 3 is 6. Still can't. It's still 5. Okay, so now let's take a look at the same graph one more time and decide what happens in the situation in which we want to use the midpoint. So this is 0, this is 1, this is 2. This piece in the middle is 1/2, and this piece in the middle is 3/2. I will draw and find the height right in the middle. And now the first subinterval, the first rectangle, the area of the first rectangle is base times height. The area of the second interval is base times height. So the area with the midpoint 2, with 2 subintervals, will be still 1 base times f of 1/2 plus still 1 times f of, that's it. So let's determine this. So f of 1/2 is 1/4 plus 2 plus 3/2 is 9/4 plus 2. So area with the midpoint 2, approximately 4 plus 10 over 4. So 16, 26 over 4, or 13 over 2, or 6.5. So we got 6.5 in the middle. We got the minimum, the lower bound as being 5, and the upper bound as being 9. Which one do you think from all these three is the best approximation of the true area? We have not determined the true area, not even close, right? The midpoint, correct. Okay, now let's say, and we are not going to do it, let's say that we started with 2 subintervals and we got for the rightmost point and the leftmost point and the midpoint. And this was with 2. What do you think will happen with 4? Will I get a better approximation of the true area if I divide the interval between 0 and 2 into 4 subintervals? Better approximation. What about n equals 6? What about n equals 600? And what about n equals 1,000? Even the best, right? I mean, even better. Okay. So first of all, let's identify what we have here in all these 3 situations. Delta x times f of x plus delta x times f of x plus, if I have more than 2, delta x plus f of x plus delta x plus f of x. What does that mean? What am I telling you? I'm telling you a sum. Correct. Awesome. From delta x times f, and this is xi because x changes. It could be the leftmost point. It could be the rightmost point. It could be the midpoint. But it changes from step to step. So from I equals 1 through n. So this will be the approximate area under f of x between 0 and 2 for our example. So area approximately. Because I can go beyond 1,000, I can go to n, right? Okay. Now what do you think I'm missing here in order to write the equal symbol? I'm missing something. By the way, this is called, this product with the sum in front, Riemann sum. The mathematician who developed it. Riemann sum. But I would like to, and that's my target, I would like to be able to change this symbol, which is an approximation, into this symbol. So I'm missing something that we discussed this semester from day 1 till today. And say it again. Thank you. As n approaches, of course. And you agree that delta x is b minus a over n, and it can go in front. So I can rewrite this as limit as n approaches infinity from delta x, I equals 1 through n from f of xi. Xi being the leftmost point, rightmost point, or midpoint, it doesn't matter anymore. So, one sentence we have to write before we look at our first example. The exact area under the graph of f of x on the interval a comma b is given by the what? Limit, very good, of the Riemann sum. The exact area under the graph of f of x on the given interval, whatever it is, a comma b, is calculated with the limit of the Riemann sum. However, this sounds very nice, and it is. We are limited. We cannot algebraically calculate the limit of the Riemann sum for anything else but linear, quadratic, cubic functions. Why? Because we only have these four formulas. We don't have anything else. For I, which is linear, for I squared, which is quadratic, and for I cubed, which is cubic. That's all we have. Cannot determine anything else. If you say, find the limit of the Riemann sum for a function that is sine x, I'll say, sorry, can't. Find the limit of the Riemann sum for arctangent. Sorry, can't. That's the only thing we can do. For either a linear or quadratic or cubic function. So let's choose one and do it step by step. Any function you want that is linear, quadratic, or cubic, nothing else. We are limited. You want which one? Oh, we can, why don't we determine this one first, the x squared plus 2. How is that? Okay, so let's say we pick x squared plus 2. And let's say the interval is 0, 2. So we're asked to determine the exact area under this graph between 0 and 2. We have to be given the function and we have to be given the interval. Otherwise, we don't know where to calculate the area. Okay. We have 3 preps. 3 preps before we put everything together. Prep number 1. Delta x, which by definition is b minus a divided by n. In our case, 2 minus 0 divided by n, or 2 over n. Second prep, and I have to explain the second prep. We're not ready. Here is the interval a comma b. In our case, 0, 2. And I will divide it into how many subintervals? N, right? N. So this is the first one, and this is the second, and this is the third. This is the ith, I plus 1, n minus 1, and n. So this is the delta x, this is delta x, this is delta x, this is delta x, this is delta x, delta x, delta x. So this point, the leftmost point, is also called x0. The first one will be x1, and then x2, and then x3. And then xi and xi plus 1 and xi plus 2, xi plus 2, and then xn minus 2 and xn minus 1, and the last one is xn. Now, knowing that this is 0 and this is 2, what will you say? How much is x1? 0 plus 1 delta x. What about x2? x2 is 0 plus, very good. What about x3? 0 plus 3 delta x. I want the last one now. And before I want the last one, I want the intermediate one. And then the last one. What about xi? Of course, I goes from 0 to, from the first one, from i equals 1 through n. What is xi? Plus? Awesome. And the last one? Very good. So this is my second prep, xi, which in this case is I times 2 over n, or 2I over n. I is from the fact that this is the ith interval. Delta x is 2 over n, so I times 2 over n, or you can rewrite it as 2I over n. So that was my second prep. Now my third prep and the last one. I have to find f of xi. I'll copy f of x right here on the side again, x squared plus 2. But I need to determine f of xi. Very good, awesome. Thank you, Nick. For I squared over n squared plus 2. Now I put everything together. So number 1, I needed to determine delta x. Number 2, I needed to determine xi. Number 3, I needed to determine f of xi. And now I can put it together. The limit as n approaches infinity from the sum from I equals 1 through n. I should have put delta x in front, but that's okay. I'll take it out in a minute. What is delta x? Awesome. Multiplied by f of xi in parentheses 4I squared over n squared plus 2. This is a constant in front. It's a factor. It does not depend on I. It will be put in front of the summation notation. Limit. N approaches infinity 2 over n. And now, once this is out of the way, what was the first property of the summation or sigma notation we looked at? The sum of ai plus bi. The sum of ai plus the sum of bi. Okay, so the sum of 4I squared over n squared from I equals 1 through n plus the sum from I equals 1 through n of 2. Okay, now let's take a look. We have only 4 summations. However, this is not cleaned up yet. As you see, this is a constant, like this one was, which will go in front of the summation notation. This is a constant multiplied by 1. This constant will go in front of the summation notation. So this is limit as n approaches infinity 2 over n, 4 over n squared, the sum of I squared from I equals 1 through n, plus 2, the sum of what from I equals 1 through n? Very good, awesome. Equals. At this point in time, this piece as well as this piece will be replaced. And we have the formulas. What do I replace this by? This one.
Yeah.
Very good. What do I replace this by?
In parentheses n plus 1 this one. Okay.
So this is n plus 1 to n plus 1 over 6. Now you know why we looked at those 4 formulas or summations for this. So this equals limit n approaches infinity 2 over n, 4 over n squared times n plus 1 to n plus 1 divided by 6 plus 2n. Now I look in brackets and see if I can simplify anything. And I see I can simplify an n with an n. And I can simplify by 2 and get 3. I rewrite limit as n approaches infinity 2 over n. And in brackets I need to distribute these two. So the denominator is 3n, and then plus 2n. And I have to distribute 2, but I have to multiply these first. N times 2n is 2n squared times 2, 4n squared. N times 1, n plus 2n is 3n times 2, 6n. And plus 1 times 1 and times 2 is 2. Let's take a moment and make sure that this is okay. So n times 2n is 2n squared multiplied by 2, 4n squared. Positive n plus 2n is 3n multiplied by 2 is 6n. 1 times 1 is 1 multiplied by 2 is 2. So far so good? I need the least common denominator here, which is limit as n approaches infinity 2 over n multiplied by, what is the least common denominator? There is only 1. So this one needs to be multiplied by 3n. So 4n squared plus 6n plus 2 plus 6n squared. Is this okay? Yes? Okay. So towards final step. So 4n squared plus 6n squared is 10x squared times 2, 20n squared. 6n is alone times 2 is 12n. 2 times 2 is 4, and 3n times n, 3n squared. From pre-calculus, we know what happens when we determine the limit as n approaches infinity from same degree over same degree. You can say, I don't remember. Fine. If you don't remember, what will you do? The top goes to, the bottom goes to, then no problem. Limit as n approaches infinity. The top is plus 12, and the bottom is
6n.
good. The top goes to the bottom goes to good. So then limit as n approaches infinity. The top is and the bottom is 6, and the answer is. I was hoping you would say, okay, since these two have the same degree, must be the leading coefficient over the leading coefficient, but that's okay. So 20 divided by 3 is approximately 7, is less than 7. It's approximately 7. Let's see what we got with our approximations. We got the upper bound to be 9. We got the lower bound to be 5, and the midpoint was 6.5. And actually is,
6.66.
yes. So quite a good approximation using the midpoint. Are we always going to do this? No. No. We will have a much easier method to determine the area under a graph. Let's, since we have another 7 minutes, let's get one other started. Yes, James, go ahead. Yes, that's fine. I will see you on Tuesday. Please come in early if you have questions, okay? Please. Yes, you did tell me. So let's get one started and you can work on it after the test. Okay. Now, if we use x cubed, which is fine, if we do not use a starting point at 0, it's going to take forever. Because we will have to take 5 plus something to the 3rd power. So if we want to do that, that's fine. But just keep in mind it's going to be a lot of work if we don't start at 0. If you want to make it easier, let's start at 0. Okay, so let's say f of x equals, let's say 2x cubed plus x, if you want, minus 1. And let's say the interval is 0, comma, whatever you want. As long as it's 0, it's still okay. 3, perfect. Remember, we have 3 preps. What is the first prep? Very good. Delta x, which is 3 minus 0 divided by n subintervals. We need n subintervals because we will let n go to infinity. Clear? So that's why this is 3 over n. Number 2, the next prep is xi. Xi is 0 plus how many delta x's? Yes, but this is the somewhere, anywhere. I, delta x. If I is 1, then I have x1, which is 0 plus 1 delta x. If I is 5, then I have 0 plus 5 delta x. If I is n, then I have 0 plus n delta x. Okay, so this is I times 3, so it's 3I over n. The third prep is, and it must be, f of xi. All these preps are part of the Riemann sum. Okay, so what we have? We have 2 multiplied by 3I over n everything cubed plus 3I over n and minus 1. 3 cubed is 27 times 2, 54. So this is 54 I to the 3rd over n to the 3rd plus 3I over n minus 1. I have all the necessary preps now. I can move on to the area. What do I write for the area?
So,
Limit, yes. N approaches infinity. From the sum, from the first subinterval, from the first rectangle, from the first area to the last one, from delta x, which is 3 over n, multiplied by f of xi, which is, in parentheses, 54i cubed over n cubed plus 3i over n minus 1. I will bring 3 over n outside. I will distribute these to 3 terms, moving the constant outside. The constant outside. Is that okay? Okay. So limit. Sn approaches infinity. 3 over n outside. Bracket. 54 over n cubed, the sum of I cubed. Plus 3 over n, the sum of I. Minus the sum of yes, it will be n, but right now I will write it as a sum of 1. In the next step, I have to replace this and this and this. What do I replace the last one by? What do I replace the middle one by? And this is easy. If I remember this one, this is squared. So I'm going to write it as n squared, n plus 1 squared, divided by 4. So now at this step, the summation notation goes away. It gets replaced by what it equals to. Okay. So this is limit. Sn approaches infinity from 3 over n. In brackets still. 54 over n cubed times n squared n plus 1 squared over 4 plus 3 over n times n plus 1 over 2 minus n. Do not start simplifying too much because then we have to multiply. So look at all these 3 fractions. There is nothing I can do here. 2n should be okay. And here all I want is to eliminate an n squared with an n squared. And I want to keep 2n, so I will simplify only by 2. I can only simplify by 2 anyway. So then limit Sn approaches infinity 3 over n. What is the least common denominator? Of the first fraction is 2n. Of the second fraction, it happens to be 2n, 2. And then I will multiply this n by 2n. And that will be negative 2n squared at the end. I have to square this and distribute 27. Let's write 27 and in parentheses n squared plus 2n plus 1. Here I have to distribute 3n inside. So plus 3n squared plus 3n. And then minus 2n squared. I can stop because it's, oh, actually I have 1 more minute. So then the limit, Sn approaches infinity, 2n squared, let's see what we have. 27n squared plus 3n squared is 30n squared, multiplied by 3, 90n squared. 27 times 2n, oh, sorry. 27 plus 3n squared is 30n squared, minus 2n squared is 28. Let's not jump and rush. That's when I mess it up. So I'll copy 3 outside. It's going to wait. So 27 plus 3 is 30. 30 minus 2 is 28 n squared. Then 27 times 2n is 54. So plus 54n. And then plus 3n. And then plus 27. You can already give the answer. If not, with 28, right? So it's 3 times 28 plus 3 times 57n plus 81. So it's this. So it's 3 times 14, exactly, 42. Very cumbersome. Very. We only look at one problem like this for the next test or final, of course. Very cumbersome. But we will learn